Hi, you guys. Welcome to your video notes for these Chapter 7 review topics. So these are topics that were not in Chapter 7, but are from previous chapters that will be tested on the Chapter 7 test. Just like in every chapter test, you see those review topics. So these topics, I wanted to spend time doing examples for you here on the left-hand column, and then you guys are going to complete the problems on the right-hand column by yourself. I started this and then had to start over. So I started this one already. Just hold on before you jump into that. I want to remind you that my goal is to keep this to 20 minutes. And for that reason, and also because these are not new concepts. So you guys have been introduced to these. I'm not teaching you anything for the first time, rather just reminding you of the processes. So I'm going to be going at a quick pace. Pause the video as you need, stop it, rewind it, replay it, make it work for you. So I'm going to start. We've got two examples solving inequalities. Here, a basic inequality with a variable and the inequality. And then on example 2, we have solving absolute value inequalities. The strategy is different for these, but they start off initially the same way, which is determining the boundary point. So a boundary point for an inequality is where the solution begins. So when you solve for B here, the solution is going to be B is greater than or less than some value. So starting at that value and then to the right or left of it. So that's the boundary point. First, we determine the boundary point by rewriting this instead of the inequality as an equation with an equal sign, and then solve for B. So first, I'm going to subtract 4 from both sides. 10 minus 4 is 6. Divide both sides by -2. So positive 6 divided by -2 is -3. This is my boundary point, meaning that's where my solution starts at -3. Since I was solving an inequality originally, and it's strictly less than, not less than or equal to, my solution starts at -3, and I'm going to put an open circle there because it does not include the boundary point. So since it was strictly less than. Now my solution is either going to be to the left or to the right. So to figure out which way, you need to test a point on either side of -3. I'll start by testing my favorite point, which is 0, because plugging 0 into an inequality is pretty easy. So we're going to plug it right back into the original inequality. So test 0. When I plug 0 in for -2 times b plus 4, that is going to be 0. -2 times 0 is 0, plus 4. Is that less than 10? My original inequality. Is 4 less than 10? Yes, it is. So this initially, right away here, I can see that greater than -3 is my solution. To be sure it's not in the other direction, I can just test another point. So I could test -10. That's an easy one because -10 times -2 is positive 20. Plus 4, is that less than 10? No, that's not less than 10. So now I'm certain that my solution is everything greater than -3. So my solution is x is greater than -3. Just a quick review on that, and I want you to try this one on your own after this video. So again, write it as an equation first, find the boundary point, and then test which side of the boundary point is the actual solution. So now moving on to an absolute value inequality. Solving an absolute value inequality begins in the same way. Rewrite this. It starts as greater than or equal to. We're going to start by finding the boundary points and rewrite this as an equation to find those boundary points. So the absolute value of 7x plus 4. Let's find out when that equals exactly 74, and then we'll figure out where it's greater than or equal to 74 after that. Okay. Absolute value, remember, is distance from 0. So if I'm talking about whatever's on the inside of this absolute value being 74, it is this whole thing, 7x plus 4, is 74 units away from 0. That means 7x plus 4, if it's exactly 74 units away from 0, then it could be either positive 74 or the other number that's exactly 74 units away from 0, which is -74. So absolute value equations split into these two possible routes to find x. Either it equals the positive value or the negative value of whatever the absolute value equals. Now I solve each one of these equations to get the boundary points. So first here, I'm just ignore the one equation, focus here on the one on the left. Subtract 4 from both sides. You get 7x equals 74 minus 4, which is 70. Divide by 7, and we have one boundary point of x equals 10, not 7. Oops. Okay. X equals 10. Okay, the other boundary point, subtract 4 from both sides. So we have 4 that I'm subtracting from 74, negative 74, I mean. Negative 74 minus 4 is negative 78. Now I need to divide that by 7. So negative 78 divided by 7. That's going to be a decimal, which is fine. Negative 78 divided by 7. Negative 11.1. We'll just round to the nearest tenth for this one. Okay, these are my boundary points. So now that I have my boundary points, I am going to test values that lay in between these boundary points on a number line. So if these are my boundary points and my solution, or I'm looking for the solution to see when my original inequality is greater than or equal to 74, we know that it equals exactly 74 at these two values. So I'm going to use filled in circles here. And now I want to figure out which way do I shade. Do I shade on the outside of these 2 points or do I shade in the middle? And we're going to have to test some points to figure that out. So I am going to need a little space here. So let's find out if something less than negative 11 works with my original inequality. It all goes back to my original. So let's do, I'll do negative 20. So test negative 20 first. I like to do simple numbers to multiply by 7. I can multiply 7 by 20. That would be 7 times negative 20. So 7 times negative 2 is negative 14. So 7 times negative 20 is negative 140 plus 4. Is that greater than or equal to 74? So negative 140 plus 4 is negative 136. Is the absolute value of negative 136 greater than or equal to 74? And that's a definite yes. This absolute value is 136, which is larger. So that worked. So a value less than negative 11 made my inequality true. So less than negative 11 is part of my solution. So I'm just shading that in. Now to be sure that the middle does not work, I'm just going to test 0 really fast. 0 is a fun one to test. 7 times 0 is 0. Add 4. Is the absolute value of 4 greater than or equal to 74? I tested 0. No, it's not. So that is not part of my solution. Now test something greater than 10, so I'll test positive 20. When I test positive 20 up here, 7 times 20 is 140 plus 4. Is that greater than or equal to 74? Is 144 greater than or equal to 74? Yes. So I see visually my two solutions are on the include my boundary points and then on the outside. So how do I write that algebraically? X is less than or equal to negative 11.1, or X is greater than or equal to 10. So that is my solution. Algebraically, how I write that, graphing it on the number line is, I kind of already did. Negative 11, that's negative 10, so maybe right here. So on the number line, that's my solution. Moving on to solving square root equations. So it's been a while here. To solve these, just a reminder, you need to isolate the square root. This one is already isolated, meaning on the left side of this equation, the only thing I have is the square root. Now it's time to undo that square root. So think about how you're going to undo square roots. I square both sides. So when you have the square root of something and then you square it, that undoes the square root. So you just result in 6b plus 19 on the left. On the right, I have b plus 2 squared. This is not b squared plus 4. Remember, it's b plus 2 times b plus 2. So you need to distribute, which would be b times b squared, plus 2 times b, plus another 2 times b. So that's 4b plus 2 times 2, which is 4. So it's not just b squared plus 2 squared. Those are part of my result, but the 4b is also a part of it. Okay, now I have a b squared. This tells me I'm looking at a quadratic and I want to get everything on one side. So I'm going to actually subtract 6b from both sides. So that's going to be b squared. 4b minus 6b is negative 2b. And then subtract 19. So 4 minus 19 is negative 15. Now I have a quadratic that equals 0, and I can do one of two things. I could factor, or I could use the quadratic formula. When it's possible to factor, I like to factor. So let's review that. So I'm looking for two numbers that multiply to negative 15, but add to negative 2. The only sets of numbers that multiply to 15 are 15 and 1, and 3 and 5. So if I want it to multiply to negative 15, that would work with the 3 and 5, because if the 5 is negative and the 3 is positive, those two things multiply to negative 15, but they add to negative 2. So the minus 5 and the plus 3 are going to be what my factors are. B minus 5, B plus 3 equals 0. Now I set each of these equal to 0. So if B minus 5 equals 0, then B equals 5, or B equals negative 3. Now, when we solve square root equations and square both sides, we often introduce something called extraneous solutions, which are solutions that appear to be solutions but are not actually solutions. So it's very important to check both of them. I'm going to check 5 first. Again, we're going to plug it right back into our original equation. So is the square root of 6 times 5, so that's 30, plus 19, equal to b 5 plus 2, 7. Is the square root of 30 plus 19, which is 49, is it 7? Yes, it is. The square root of 49 is 7, so that works. 5 is part of our solution. Now I'm going to check negative 3. Is the square root of 6 times negative 3, so 6 times negative 3 is negative 18, plus 19, equal to negative 3 plus 2. Negative 3 plus 2 is negative 1. Let's simplify. The square root of negative 18 plus 19 is positive 1. The square root of positive 1 is not negative 1. That is not true. So that is not a solution. So that's why it's super important to check those solutions on square root equations. Okay, a couple more sample types, and then, all right, so here's another interesting problem that I want you to solve by factoring or the quadratic formula. However, this one looks a little tricky at first because I have a cubic, x cubed plus 8 squared minus 33x. What we need to do here is there anything we can factor out before we begin looking at this? Now, you kind of have a huge hint because I say solve using quadratic formula. You need to pull out the common factor between all three of these terms. They all have an x. So while we don't have a good method for solving this cubic equation, we could factor the common factor of the x out. And then that would leave, when I take an x out of x cubed, I have x squared. 8x squared, when I factor an x out, results in 8x. And when I factor x out of 33x, it's just minus 33. So now I take the x out, and now I'm just looking at a good old-fashioned quadratic times x. This I can factor. This is a quadratic. So think about what's going to multiply to negative 33 and add to positive 8. Luckily, 33 only has a couple of options to multiply to it, 11 and 3. And to get those to add to 8 and multiply to negative 33, that's going to take positive 11 and -3. So that has a product of -33 and a sum of +8. So now I'm looking at this factorization, x times, so this x out front is still there, x plus 11 times x minus 3. Now, I have 3 possible solutions for 0. When this x equals 0, when x plus 11 equals 0, or when x minus 3 equals 0. So that's going to give me 3 solutions. X equals 0. This one gives me the solution of -11, and that one gives me the solution of +3. So 3 solutions there because I was solving a 3rd degree equation. All right, a couple more examples and then we're done. So exponential growth and decay. So remember, we are talking about a times b to the x. We're going to apply. Now, this isn't necessarily review. This is what chapter 7 was on, but we're going to be using some former knowledge as well. So Amy's antique bobblehead collection is so rare that I don't actually have an antique bobblehead collection, by the way. It is so rare that it is expected to increase in value by 6% a year. If it's worth $750 now, how long will it take for the value to reach $1,500 or double, basically? So let's think about this equation. How am I going to write y equals ab to the x using my information? So y equals, so my initial value a is 750. My multiplier, it's increasing by 6% a year. My multiplier is not 6%. And my multiplier is definitely not 0.06, because then if I multiply something by 0.06, it's getting really small really fast. If something is increasing by 0.06, then it's going up. Instead of being worth 100% of its value, it's worth 106% of its value. So it's actually the multiplier, you put a 1 out front, and it's 1.06 to the x. By the way, on yours, the one you do over here, it's decreasing by 9%. The multiplier is not 9, and it's not 0.9 or 0.09. It's 1 minus 0.09. So just beware of that. You'll do 1 minus 0.09 to get. Think about it. If 9% is gone, 91% remains. So that means the multiplier on that is 0.91. It's decreasing, so it's less than 1. Okay, that's a good hint for that. Okay, so the problem though is not asking for the equation, it's asking for how long it will take for the value to reach $1,500. So this is not what I'm plugging in for x. X is however long however much time has passed. So I'm actually asked to solve for how long, in other words, the time when my collection is worth $1,500. So I'm actually plugging $1,500 in to my equation. This is a new way of using an equation like this. I need to solve for x. We have new tools that will allow us to solve for x here as it's being stuck right now in the exponent. I need to solve for x. It's stuck in the exponent. How am I going to get it out of the exponent? Hopefully you're thinking of logarithms. Before you can take the log of both sides, I need to isolate the exponential piece, meaning I need 1.06 to the x by itself. So divide both sides by 750. Oops. Okay, it's gone over here, and I have 1,500 over 750. You can leave it like a fraction if you don't recognize that you can cancel out those last 2 zeros, and then you have 150 over 75. If that, you can rewrite that as 2. I'm actually going to leave it as a fraction just to show you that it's okay to work with a fraction in this. So let's say you kept it as 150 over 75 equals 1.06 to the x. Now again, I need to get that x out of the exponent. So take the log of both sides. And you can just leave this whole fraction inside the logarithm. 150 over 75, the log of that equals the log of 1.06, but the x is going to be able to come down out front. Then to solve for x, all we have to do is divide both sides by the log of 1.06. So I'm going to take this whole thing and divide it by the log of 1.06. Okay, it's going to cancel on that side, and I'm just going to be left with x by itself. Now in your calculator, it's fine. It looks like there's a lot going on here. It's not hard to type in. So first just type in the numerator, log of 150 over 75. And then you can hit enter or whatever, it doesn't matter, but use that exact value. Divide that by the log of 1.06. We get 11.89. So about 11.9 years. So almost 12 years. And then my bobblehead collection will double. Okay. This one's going to be very similar. I kept this a fraction because this, even though it reduces, 150 over 75 is 2. You could have used 2 that whole time. This one doesn't reduce in the same way. So I just wanted to model using a fraction because it's not too complicated. Last example, solving logarithmic equations. So this is a new type of logarithmic equation. I need to figure out what x is. Now, if I have a single, like if this was just log base 4 of something equals 5, then I could just do 4 raised to the 5th equals whatever is on there. But I have 2 logarithms, and I don't want 2 logarithms, I want 1 logarithm. Luckily, we have a property that allows us to write 2 logarithms that have the same base as a single logarithm of that same base. If they're being separated by subtraction, then on the inside of the logarithm, I can rewrite that as division, x divided by 2. So we're going to apply these properties of logarithms in our solving process. Now I have a single logarithm, base 4 of x over 2 equals 5. So now I can just use my knowledge of logarithms to solve for this. So this relationship means 4 to the 5th power equals x over 2. So 4 to the 5th is 1024 equals x over 2. To solve for x, all I have to do is multiply both sides by 2. So x equals 2 times 1024. So that would be 2048. And that is my solution for x. All of these examples I've just done model how you're going to do on the your turn problem. So try these, and then when you're finished with the whole thing and you've done all of your problems, please upload it to Schoology. And that's it. I will see you soon. Hope you guys have a great day.